Apologies for that. I figured it might be a little bit easier to see these screens on horizontal, so we switched back over to the horizontal format. So again, getting back here, we've got our first channel across the battery. And again, this is used to establish what the state of the battery is. This is our reference point. Channel 2, we have got the scope lead, the positive or the red or the signal is going to the back of the alternator positive stud. Then we've got the B negative or the black part of the lead on the scope back to battery negative. Again, because the Topdon oscilloscope is in fact a shared ground scope, we do not want to connect that negative part of the second channel anywhere else besides back to the same battery negative that we have channel 1 on. Again, if we do that any other way, if we connect that negative channel or the negative portion of the lead to anything else, we can create a current flow situation which can damage the scope itself. Channel 3, we're going to use an amp clamp. Now we use the amp clamp to verify and find out, is the alternator actually moving any current, right? We have to establish, is the alternator doing any work? And again, this is where we may want to check with the scan tool to verify, hey, are we actually seeing any command? Is there a change? What are we looking at, right? So the other thing we're going to look at here is our sample rate. So the sample rate doesn't need to be ultra high here in order for us to be able to pick up and interpret what's happening with the alternator itself. The more we turn up the sample rate on the scope, the greater amount of unintended noise we are going to see on the waveforms, making them potentially harder to interpret. The other thing we want to keep in mind when we're doing any scope testing, I personally like to do it two different ways. I very much like to be able to, number one, look at something at a wider time base, and number two, be able to, excuse me, be able to see at a wider time base what's happening over the longer course, but also be able to compare at a closer time base or a narrower time base. If we can see things on both shorter time bases and longer time bases, the longer time base may afford us intermittent issues. We may be able to pick off if there's only a problem occurring every so often. The longer time base zoomed out allows us to pick off things that we may not see when we're zoomed in to a shorter time base, such as 100 or 200 milliseconds. So again, we're going to demo you this on our video in just a short bit here. So keep that in mind. All right here, so turn my camera back on so you can see me again since we're now on horizontal. So basically, we'll go to the next slide here. So these are some best practices we want to keep in mind with reference to charging system tests specifically. We want to do the tests under a couple of different conditions, right? We want to start the car up. We want to capture our data with all of the electrical loads on the vehicle turned off at the beginning. Then we want to perform another test with all of the electrical loads on. And when we say on, we're talking about headlights, brights, blower motor on high, and any other electrical load that you can activate to stress the system. And again, stressing the system is crucial to being able to reveal if there are problems with the system. And this is what we would refer to as a dynamic test. If we do not stress a vehicle's system, the quality or the value of the testing that we perform may be greatly reduced, and it may also make us miss something that is present on the car if we don't stress the system or do a dynamic test. So just if we were doing any other testing, let's say we're doing ignition system testing, we would want to stress the ignition system by doing something like a snap throttle test. If we do not stress the ignition system, the data we're collecting, again, may not provide very much diagnostic value. So I typically will do 3 captures. I'll do an idle with no electrical loads. I'll do an idle with maximum load, so all those electrical loads turned on. And then I'll do a 2500 RPMs or thereabouts with all of the electrical loads turned on. And then I will look at each of the waveforms to kind of get a feel for, hey, have I found anything meaningful, right? So we do want to understand what we're looking at in each of the data. So the other thing we want to do is we want to make sure we repeat each of these condition tests at least twice, which doesn't take very much time, but we want to repeat each of these tests at least twice because this is how we establish consistency. Just like when we do any cloning stuff, as you've seen in any of the YouTube videos we've done on cloning or any other tests that we've done, the best practice is always to do each individual test at least 2, if not 3 times to make sure we get consistent results. Now, again, each way I typically do most scope testing is I'll use a wider time base, so anywhere between 50 to 500 milliseconds per division. And again, we're going to show you this on the scope. And then also, I'm going to narrow the time base down to a shorter window or a smaller amount of time on the screen, which is going to allow us to scrutinize the finer details of the given waveform. So here's an example. So here in this screenshot, we can see we're at a 500 millisecond time base. So if we look at the scope, in the middle, we have our 0 mark of 0 time. To the left, we have all the way out to 2.5 seconds to the left, 2.5 seconds to the right. So we have a total of 5 seconds of time on the screen itself. Now, as we look at this particular waveform, we're going, wow, there's just a lot of hashy, bouncy nonsense. We can't really make heads or tails of that. And that's fine. That may or may not be important for us to understand. Typically, what we're going to look at here is we're going to be scrutinizing voltage levels, right? So in this middle channel here, this purple, we're looking at a millivolt scale. In this green or light green channel, we're also looking at a millivolt scale. And in the yellow channel here, we're looking at an amperage scale. So the yellow channel is going to be alternator current. This center channel here is going to be likely something like AC ripple, right? Potentially at the alternator. Or it could be at the battery. On the top channel, we may have alternator, or we may have at the battery. Again, it's going to be different depending on your setup. So we're going to do this live on the car so you can physically see what it looks like. But here, you can see an example of when we zoom in, how we see a lot finer detail on the waveform. So this particular zoom capture, the initial capture, which is what you see in this top window here, that is 50 milliseconds per division. So again, not a tremendous amount of time on the screen. On the other hand, if you look at our zoom window here on the bottom, we're at 5 milliseconds per division. So we are zoomed into a much tighter time base here in this bottom section of the window, right? So again, we're able to look at all the little minor details of each waveform to get more of a feel for what's actually happening. Now, you're asking, well, how do I make sense of what those waveforms actually are? Well, we talked a little bit about being able to compare to other vehicles potentially, right? That's a tremendous value. I'm just going to look at, make sure I'm not missing anything in the chat. Okay, cool. Sounds like the chat's good so far. So again, we want to ask ourselves, how does this system work? We want to know if that alternator is a variable or a more fixed style alternator. Is it being controlled? Is it computer controlled? Which module is in charge of that computer control, right? We have to be able to find that information out. Now, typically that's going to be found in service information, or you can typically also hook up your scan tool, go into live data, and check to see which modules may be showing that data. And we'll see if we can show you that on the camera as well. Can we command that alternator charging state up or down with the scan tool? Sometimes we can. Also, if we turn on the electric loads, do we see a dynamic change in the command as well? Presumably, that would make sense, right? we would expect a connection between how much electrical load is being applied to the battery and electrical system versus how much command is actually being applied to the alternator to raise or lower the charging. We also need to remember, is the alternator actually receiving the command? Just because we look at the data on the scan tool and see that the alternator is in fact being commanded does not necessarily mean that the command is reaching the alternator. Again, this is a place where we can see that with the oscilloscope in a large number of situations. We also want to ask, is there two-way communication? Some alternators may be effectively just a responder in a particular control loop. Other alternators may physically send data back. For example, if we have a LIN or local interconnect network between the alternator and another module, the alternator may be physically sending data back, responding to whatever module is in charge of that charging control, and telling that module, yes, I am responding to your command of 50%, and I am in fact charging at 50%, right? So we do want to understand, is there two-way communication taking place, or is this effectively a one-way system, if there is in fact variable control? And again, let's not forget or ignore or skip over the value of the scan data, right? We do in fact want to see if we can check this in the scan data, because of course, we need to know if the command is even there first before we go hooking up the scope and trying to interpret anything at the alternator with regards to command, control, or messages. There's also a wide variety of publications out there that cover AC ripple. This is a common question. What is AC ripple as far as specification, right? What is good? What is bad? What's a problem? What's not a problem? The best guideline is if you have a symptom that could be explained by the amount of AC ripple you're seeing, there may be something at play there, right? On the other hand, it is also important to understand that some of the data that is out there related to AC ripple provides AC ripple measurements in different values. So we need to understand that AC ripple specifications can be usually provided in two different ways. Peak-to-peak AC voltage ripple, or RMS, or true RMS. They are not the same. Peak-to-peak AC voltage is what your scope is going to show you with your eyes, right? Now, we'll show you on the scope how we set those measurements up. The RMS, or true RMS, is what we typically see measured via a DVOM, or digital voltage and ohm meter. So if you find a specification on AC ripple, be careful. Make sure you understand, is this a peak-to-peak AC ripple they're talking about here? Or are they talking about an RMS or true RMS ripple? So here's the thing you want to understand about RMS or true RMS. So if we look here, peak-to-peak voltage ripple of, let's say, 424 millivolts, which is just slightly under a half a volt, equates to 150 millivolts of RMS voltage. Again, so the two measurements are scaled differently and convert differently. This particular QR code you see in the center of the screen will actually take you to the calculator. So if you're measuring it in peak to peak, you can type that in and calculate what the RMS voltage is, and vice versa. That way, if you find a specification, you can easily convert one to the other if you need to understand. So again, understanding the scaling or the meaning behind the measurement that you are taking, and also that measurement specs you find may differ depending on which way they are communicating the data. So here's an example on actually the vehicle we're going to do live today, but we'll just talk through the waveform here real quick before we translate over to actually doing this on the car. So in this particular situation, the center channel here, or excuse me, not the center channel. No, wait, yes, the center channel. Again, my apologies. The center channel under a full load, you can see I've got highlighted in this box right here. The alternator is outputting about 83 amps of current, which is quite a bit, maybe close to its maximum capacity. Again, we're pushing it, we're stressing it, We're trying to make it fault if it has a problem. And what do we see as far as the RMS value? 85 millivolts. Remember what we said here? 85 millivolts of RMS is below the generally accepted 100 to 150 RMS. Now, again, if we have a symptom, that spec could still be or that measurement could still be a problem. Again, it's going to depend on vehicle. The newer vehicles tend to be a lot more sensitive to AC ripple. The older vehicles tend to be a lot more tolerant of AC ripple. But again, understanding that the RMS value is below the generally accepted norm for this particular application and most automotive applications, this vehicle does not have any symptoms, and this RMS value, again, is below our generally accepted norm of 100 to 150 millivolts RMS AC voltage. We don't see any crazy outliers, no Waldo in the current flow. We see a few spikes here and there, but nothing too concerning. And this alternator has quite a few miles, years, etc. on it. So we wouldn't necessarily expect the waveform to be absolutely perfect, right? Now this is DC current we're looking at, not AC current. Okay. Now we do watch for these things, like these outliers here in this voltage here. And again, this is the AC channel we're looking at. If we see those outliers and we do have a vehicle electrical system problem, it could potentially be a problem with the alternator. This could also be ignition noise. So we may see AC voltage in our trace as a function of AC noise from the ignition coils. So be aware of that. If you're not sure, you can always put a scope channel on your ignition coils and see if they line up perfectly. If they do, then you know that that noise is coming from the ignition, not from the alternator. A couple other things we'll talk about, and then we're going to go straight to the live on-car stuff. Is the AC voltage we see on the screen a problem? We don't know, right? We have to ask ourselves, do we have a symptom on the vehicle? Is that something that we're chasing? Do we believe that an alternator problem would explain the issues we are having with a given vehicle? If the measurement is a marginal measurement, how could we find out if the alternator explains this? AC ripple in the alternator. We could disconnect the alternator, right? Now, you don't want to run the vehicle for any extended period of time without the alternator connected, and you want to be careful if you're going to disconnect the alternator. But it is truly important to understand that the alternator being removed from the circuit may in fact provide clarity as to whether or not you're getting AC voltage ripple from the alternator, and or is that creating a problem specifically with the vehicle electrical system, such as a module bus communication problem or any other symptoms that are potentially electrically caused, right? Now, the other thing you want to understand here is the 12-volt battery on the vehicle not only serves as a reservoir, like a tank, to store energy, but the battery also provides a damping effect to AC voltage ripple. So if the battery on the vehicle is in a poor state of health, and remember, we talked about dynamic battery and starter testing on the last webinar, if we do not understand that the battery being in a poor state of health could be a factor in allowing more AC ripple to reach said components, then we need to make sure our battery is good before we make any diagnostic judgment call on what we are testing with the AC ripple and the alternator system. So again, very important to keep in mind. If you have suspicion that there may in fact be an issue like that, like a battery problem, you may want to recommend or replace the battery before carrying out any additional testing. Now, if we are going to replace a battery, one thing to keep in mind is if you get a new battery, doesn't matter where you order it from, always make sure to charge your brand new battery before you put it into the vehicle. It's also important to keep in mind a lot of modern vehicles also have some form of either battery coding, where you have to tell the vehicle the battery was replaced, or potentially resetting of a charging algorithm. Many new vehicles have an adaptive charging algorithm that is executed by the module that controls the alternator's charging behavior. Now, your scan tool is going to be the ticket to performing those resets. And again, reading service information will typically make you aware of those requirements. But if you do not reset those charging algorithms, typically what will happen is the alternator will be commanded to overcharge a new battery, and you will eventually end up with a prematurely failed battery. Now we're going to skip through this just a little bit here. Now here's just another illustration of the difference between RMS versus peak-to-peak AC voltage ripple. Here we're zoomed out at a wide time base, and it's important to keep in mind if you use the measurements here on the scope, it's going to be looking at it across the entirety of what you have on the screen, not one single moment in time. So be aware of that. This is going to be essentially averaging it out over the course of the whole thing. So if you see a small section of the waveform that happens to look questionable, make sure you zoom in to put only that segment on the screen and then look at your measurements down here again. So here is another example. Look right here. Remember we said half a volt peak to peak is where we might be in trouble or we might start to have a problem. We're still below the 100 millivolt range of RMS AC ripple. And now we are ready to go transition over to showing you some of this on the vehicle. So I'm going to stop screen sharing. I'm going to turn on my secondary camera and I'm going to switch over here so you can see. So the first thing I want to show you is scope leads. Now many scope leads are going to come with grounds attached to every single channel. And again, we talked about the fact that the Topdon oscilloscope is a shared ground oscilloscope. So that means every single channel's ground side of the given channel is connected to every other channel's ground side connection. So again, that's important because we can damage our scope if we're not careful. I'm going to take you over here and I'm going to see if I can I'm going to probably hold it up to the main camera so you can see it well. But essentially, there are different types of scope leads that we can purchase in order to accommodate protecting the scope. So if we look closely at this particular lead here has a detachable ground. So what that means is we can take the ground off of this channel. That means we can now plug in the signal side of the scope channel directly into whatever we want to measure or look at, and we don't have to worry about accidentally connecting the ground to a different ground other than battery negative, which will protect the scope from being damaged in the course of scoping. Most other scope leads typically do not have detachable grounds. The grounds are simply always connected as far as to the main lead itself that goes back to the scope, the BNC connection. However, you can simply leave that black lead that is next to your colored lead disconnected from the car in order to achieve the same function. It's just convenient if you do have a detachable ground, because again, we don't need those grounds on the other channels if we have one of our channels connected straight to battery positive and battery negative. Okay, so just something to keep in mind there. So now I'm going to switch over here. And we're going to go to the primary camera so you can see what we got set up. Now, I did not connect a scope channel specifically here for the alternator AC ripple yet, so I am going to do that. And on this particular car, it is a little bit more challenging to be able to get the channel to clamp onto the very back of the alternator stud. And you will find that when you are scoping vehicles and trying to connect to the alternator stud, you may face a few challenges being able to get those clamps to kind of stay on, right? They do have kind of a tendency to want to fall off, and you got to be a little bit careful about this. However, it is very important that we do, in fact, capture the ripple directly from the back of the alternator, ideally. That is our goal. So we'll see if I can get in here and get this connected. I have done this capture or this test on this vehicle before, and I do believe I'll be able to get in there and get it again. It looks like I should be able. So I'm going to connect this third channel here, again, directly to the back of the alternator positive stud. All right, so assuming I have all my connections correct here, we're going to take you back over and I'm going to do screen share with the scope so you can see what I have as far as the setup goes. So let me switch here, get the scope program open, and we're going to share. All right, so now you can see the scope. Now we have the scope stopped sharing at the moment. So what I've got set up on the actual scope itself here, let me make sure I can, okay, we're going to do this. And, okay. Can you all see the scope window? I'm going to switch that. So I'm just looking here. I want to make sure you can all see the scope window effectively. Okay, so you cannot see the scope window effectively. All right, I want to fix that. Place. There we go. All right, now. Okay, that is not working correctly. Whoop, 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 maybe. Come on now. Can you see it now? Sweet. Okay, so now you can see the scope. Good. That was the goal. So on the scope here, how we're going to set this up, I've got the very first channel on this connected to battery positive and battery negative. So again, this is a scope that has both a colored lead and a black lead. The black lead is going to battery negative, and we'll take you to the car to show you that. And the colored lead, which is blue, is going to battery positive. The second channel here is going to be an amp clamp. Now remember, we're going to go to AC voltage because we want to look at, actually, you know what? We'll start out with DC voltage at the battery. So we got DC voltage on channel 1. We're going to leave it on voltage probe, and we're going to leave it on ×1. We're going to turn on the filter, which is 20 M, as you see down here. Then we're going to go here, and we're going to change this to current. So channel 2 is going to be our charging current from the alternator. Now that's going to be DC current, and we are going to have to change our scaling accordingly. And we'll do that live when we start the car up. Third, we're probably going to need to change the scale since this alternator is probably going to put out somewhere in the neighborhood of 80 to 100 amps, right? And then channel 3 is going to be our AC voltage ripple at the alternator stud. So we're going to go AC, and it's voltage, and it's 1 times, and we're going to turn on our filter there. So we got all the channels configured. So now we're at 500 milliseconds for time here. So you see our time settings right here. Again, that's 500 milliseconds per division, so half a second. And we're going to change our sample rate. Up here we have 10,000 samples is our targeted sample. Our effective sample rate is 2,000 samples per second. We want to raise that. We're going to raise it to 1 million or mega, and we've got 200,000 samples per second here. So now we're going to hit run, and we should have some waveforms on the screen while everything is connected. We do not know if we have our amp clamp scaled correctly yet. We can ballpark this pretty easily by taking an easy shot in the dark once we get the vehicle started. So at this point, we're ready to start the vehicle and start getting our channel settings tweaked. So I'm going to open my garage door so I don't die of carbon monoxide poisoning here. So bear with me for just a moment. And I also need to turn on the amp clamp and make sure it is fully zeroed. Of course, I leave the amp clamp off since it's powered by a 9-volt battery. And that's another thing we want to be really careful about is making sure the batteries in our amp clamps are good. So here you see we've got the amp clamp. We're going to turn it on. Make sure your battery light or your power light comes on and your low battery light, if your amp clamp has one, does not start blinking or light up. Now we also, some amp clamps, which you can see here, I'll put you in the camera so you can see a little better. Some amp clamps do in fact have a zeroing function on them. So you want to make sure that when you have your scope set up, that your amp clamp is properly zeroed out. And a lot of amp clamps may not have a dial like the one we're dealing with right here. So if you do not have a dial, then you definitely want to make sure that you are zeroing it out to the best of your ability. And also keeping in mind, all right, so we're going to change everything here. Now, I don't know if the scaling on this is going to be correct, but we're going to find out here. So it looks like my amp clamp is not zeroed, which is not surprising. That is often the case when you first turn them on and have to make adjustments. So my zeroing function doesn't seem to be working, which is a problem. That's pretty weird. Wonder if I don't have it screwed in all the way. I'm going to screw it into a different channel here. We'll just make sure. Hopefully I'm not having a channel problem, right? All right, so we're going to switch to channel 4 instead of channel 2 here. And we're going to go looking at current. And I was just traveling, so it's always possible that my scope got damaged in transport. Unfortunately, that is a reality we do potentially run into, right? I'm going to change our scale here. All right, so there we go. Amp clamp looks like it is good on that. I'm going to change the scale. Okay, so we'll bring it down. I'm going to move that all the way down here. And there we go. All right, so now we're going to start the vehicle up. And we're going to see if we have everything dialed in, which most likely, when you first go to start up, you're probably not going to. Now we're going to start up with no electrical loads turned on. Everything is going to be turned off ideally here. No headlights, no blower motor, none of that stuff. All right, so that channel is connected. So we have got we're going to change our scaling here. And that is AC voltage. Okay? And our amp clamp is either dead or I've got a scale wrong. Probably scaled wrong. We're going to find out here. Usually the case. Scaling is the problem, right? You know, you'd think I would write down my scaling for stuff, but I have not. All right, let me get our other channel for battery voltage back down on the screen here. Okay, so we can switch this over here, change this to AC voltage. And look at that, when we change it to AC voltage, we don't have a bunch of AC voltage there, so that's a good sign. So now, I think my amp clamp might be dead, so might not be able to get current on this one. I'm just going to turn off this. I'll have to investigate what happened to my amp clamp later. But what we're looking at now is, again, this is a wide time base. So what we have as far as channels go is This first channel here, this yellow one, is AC voltage. Currently, I switched it back to AC voltage. AC voltage here, back at the battery. Then, our red is AC voltage at the alternator positive stud. So, we don't know if this is good or bad yet. We're going to change our signal range. So what we're going to do is, we have no loads turned on or minimal loads turned on right now. We're going to stop the capture right here. Then we're going to go into our menu in the top here. We're going to click Measure, and we're going to go Channel 1 first. And what we want to do is we want to look at RMS and peak to peak. If I can find it. Of course, my brain's not firing on all cylinders at the moment. There it is. Okay. So now, if we just drag the screen back and forth, it'll complete the measurement for us. So we have RMS, 47.75 millivolts. Not much, right? That's not high. Peak to peak, it says almost a volt, but that's because it's looking at these humongous spikes, which again, may be simply coming from the ignition system. Now, another way you can potentially interpret this is we're going to go and look at the bottom channel here. And again, we're going to make the same measurements. So we're going to click on channel 3, go to the menu, measure, channel 3. And again, we're going to select peak to peak, and we're going to say RMS. And again, we're going to move the screen just a tiny bit back and forth. Okay, RMS 198. Uh-oh, that could be a problem, right? Now, is our channel set up correctly? Yes, AC. That could be a problem, right? We don't know. What we want to do now is zoom into a section of the waveform, and you can see how the measurements are changing as we zoom in. Okay, so you see now we're right down to 100 millivolts right here. And remember, this is coming right off the back of the alternator, so 100 millivolts of AC ripple. That's right at the threshold where we may be starting to encounter an issue with this alternator. But this particular vehicle is not having any symptoms at all. So there's no reason to believe that this is a problem at this point in time. Now we see here, back at the battery, there's a little bit higher measured number, right? RMS though, not so much. So again, it's looking more at these big outliers, why we get the higher peak to peak. Now for me, what I'm typically going to do is look at RMS. Ultimately, RMS is like an averaging over time, which you can look at in that QR code that I shared to get a better level of understanding of which measurement is probably the better one to look at. For me, I'm typically going to turn off peak to peak and just look at RMS. Because ultimately, the RMS is what I'm most concerned about. So back at the battery, we only have 26 millivolts right here. That is not a big problem, right? I'm not concerned about that if we're that low back at the battery. Remember, the battery is what's going to be feeding all of the different components on the vehicle. So this battery is doing a good job of dampening AC voltage. You can also see here, we're not even putting out a whole lot of AC voltage. And even though it's right near the spec of 100 to 150 millivolts, we have no symptoms. And because the battery is dampening it effectively, this is not a problem on this vehicle. So again, you can also see we're zoomed into 50 milliseconds now, where we're actually scrutinizing the waveform in detail. You can go tighter here and look a little closer. So look a little closer, it cuts it down to even less here on the alternator. Again, that's the B positive stud on the alternator we are connected to. Now, this is the no load situation. So what we're going to do is, we're going to go back out to 500 milliseconds. We're going to turn this capture back on, and now I'm going to turn a bunch of the electrical loads on so you can see what happens to the waveform when we turn on electrical loads. Here's our headlights on. Not much of a change on the purple trace on the bottom there, or pink, the alternator. Let's turn on the blower motor. Okay. Still not a tremendous difference there. And we'll turn on the radio. So again, what we're looking for is changes over time, right? So now we're at a situation where we have a pretty significant electrical load on the vehicle. All the main electrical accessories have been turned on. We're still at idle. We didn't see a massive increase in the amplitude for the most part. We're going to stop though. We're going to make sure that we go in. And again, back at the battery, we still only have 64 millivolts. So that's not much, right? That's still below the spec. When we go out here and we zoom out, now look here. We go into 50 milliseconds. We do see here on the alternator 150. So we might be starting to get an alternator here that could be becoming a problem down the road. However, since there are no symptoms present at this moment, we don't have any diagnostic criteria we can use to recommend replacement of the alternator. Here at the battery, we still only show 45 millivolts of AC ripple, which is not a problem. So what the vehicle electrical system is truly being exposed to here is still pretty limited. And therefore, even though the alternator may be approaching the level of having a problem, the vehicle's electrical system is being properly protected and isolated by a good battery. So, good to understand that. If we zoom in even further, you see the net measurement comes down just a little bit more. Not a lot of impact on the battery trace, but a little bit more effect here on the alternator trace when we zoom in. Again, it's averaging this over the course of what we see on the screen. Now, I'm also going to zoom you back out to 500 milliseconds so you can see what happens. I'm going to rev the engine up to 2,000 RPMs, or roughly 2,500 RPMs. And I'm going to click stop here so you can see. Now what we're going to do is drag this back just a little bit here. We're going to zoom in right here. So here's the spot where I was revving the engine a little bit more. See how the waveform looks a little bit more on the dense side. Zoom into 50 milliseconds here. Again, it climbs a little bit. So we were at about 154. Now we're up a little bit higher here, right? 165. But at the battery itself, we're still seeing substantial dampening of AC voltage. So there's really no reason to suspect we're going to see any symptoms, which of course is good news. So again, you can see being able to test this under multiple conditions and look at our AC measurements, not only at idle with no loads, or at idle with loads, and also at 2,500 with loads. And if you've used a conventional or a simple battery tester, you've probably noticed you've been asked to do testing in a similar fashion when you are dealing with the simpler automated battery or alternator testers. So again, pretty straightforward. So I'm going to go ahead and just capture a little bit more at idle here and then stop. And then I'm going to take you over to the camera and stop sharing that. We're going to take you to the camera here so you can see how I've got this set up. So, attempt to show you. So, basically what I've got here, again, you can see over here in the scope, I've got the blue lead here. The blue lead is across the battery. So again, the colored lead is on positive. The ground or black lead is over here on battery negative. That's channel 1. Channel 3, which is the green, that is going, if you can, well, you probably can't see it, but if you could see it, that is over at the back of the alternator. And again, that channel does not have a ground attached. See if I can take you with the camera to show you a little bit closer here. I'm going to shut off the car here in a minute too, so you can hear a little better. But see if we can kind of zoom you down in here with the camera. Down inside here, basically we're connected right to the back of the alternator stud, right here. And again, that's just the signal, the green part of the lead. That is the only part that is connected here on that channel. If you look right here, I've got the ground portion of the green channel is removed. So we're just using the signal portion of the channel, and that is going back to the third channel on the scope here. Agreed. Now we were trying to do the amp clamp, but apparently my amp clamp decided to give up the ghost, or the battery maybe is dead. I didn't think that it looked dead, but again, unfortunately, sometimes we run into issues. Why we got to check our equipment with some level of regularity, right? And I just used this amp clamp the other day, so I'm a little surprised and disappointed that it's broken. Nonetheless, this was not a very difficult or time-consuming test to rig up on this particular car, but we do want to keep in mind that whenever we're doing this type of testing, some vehicles are going to be much harder to set up the back of the alternator test, right? So reaching the battery positive stud at the alternator may be uniquely challenging on certain vehicles. So we do want to understand that that can take more time, be more challenging, etc. But hopefully you've been able to see this is not overall that difficult of a test to perform, assuming you can access the connections on the vehicle. As long as you can reach the backside of the alternator and set up the AC ripple test there, as well as testing at the battery, then we can do this test with some level of efficiency and effectiveness that will ultimately produce some good information. Awesome. So we are essentially at the end of our time window today. So I'm going to, all right, there we go. So we're going to actually kill the other camera here. So what we took you through today was essentially a follow-up to our last video. And our last video was talking about batteries and starter testing on vehicles. So today what we showed you was how to check the charging system, which is the 12-volt electrical system on the vehicle. We did not have a chance to go through the scan tool portion. And again, it is important to remember that when we're doing the scan tool portion to check the command, we do want to make sure we understand, is the alternator being commanded to charge at a certain amount, or is the vehicle turning it off? And alternators today can, in fact, literally be duty cycled off almost in their entirety, which is something a lot of folks are kind of taken surprised by. So just something to keep in mind when you are dealing with this. It's very important to understand that the alternator can essentially be turned off while you are driving, and also at idle, just depending on the state of charge of the battery and depending on whether or not the vehicle has a good battery in it. It's also, again, we want to remember vehicles, when there's any kind of repair that's been done to the electrical system, specifically the battery, we want to understand if there's a vehicle requirement that says, hey, we need to make sure that we code this battery to the car, or that we reset an adaptive charging algorithm, which is going to be part of the charging system. So again, all of those things are very critical to understand, and make sure you're reading the service information so you have a good awareness that this may be something on the vehicle you're working on. So just want to say thank you for joining us here on the webinar. I'm really glad that you had an opportunity. Of course, this is recorded and it's going to be on the YouTube channel. So we really appreciate you taking the time to watch either live or on the recording. And as always, I'm Hawken with Topdon. We'll see you on the next webinar, and we'll make sure to let you know what the next topic is going to be.